Sir, you are not audible, sir.
Is it? Hello?
Now
Your
it's fine,
voice
sir.
is not audible.
What?
No, your voice is not audible.
Is it okay now?
It is okay now, sir.
Okay. Should I start from the start?
Yes,
So
sir.
we are dealing with the transport properties or thermal properties. Okay. So thermophysical properties, under that we call some of the properties to be transport properties. So first of all, we will try to understand what do you mean by transport property. These are the properties which are basically the reason for the response of a material to any changes that are happening outside of it in the form of temperature, velocity, or composition. So if a sudden change in its surroundings happens, how it reacts is what is basically responsible. Properties are called as transport properties. The properties which are responsible for the response of a material for a sudden change in its surrounding environmental or any physical changes happening outside, not physical, any changes happening outside in the form of temperature, velocity, or composition, etc. So those properties we call it as transport property. So for example, we have a copper bar and we have a wood. Both are having same thickness, same height, for example. Suppose if I am heating it on this side, if I am heating it this side by certain amount of temperature heat flux Q, which is 10 watt per meter square, for example. So when I give this particular temperature, this side there is an increase in the temperature and there is a difference in the temperature. So let us say that this is around 50 degrees centigrade because of the heat flux, its temperature has raised to 50 degrees. Initially, the room temperature is 30 degrees centigrade, let us say. So now, because of the heat flux, the temperature has raised to 50 degrees. So on this side, it may go up to 45 degrees or 40 degrees centigrade, for example. Okay, when under steady state conditions, this might have happened. Whereas for a wood, if you do that, it may be same Q we have given 50 degrees centigrade, the temperature on this side, but the temperature on this side may be 30 degrees, 32 degrees centigrade, just above the ambient temperature, 30 degrees. So both are two different materials, and there is a property of these two materials which is actually responsible for the variations in the outer surface temperatures. Okay, one side the temperature has changed and the amount of energy that is given on one side is being transported to the other side. Okay, is being transported to the other side, and how quickly it happens or how slowly it happens is dependent on a property of this material, which are called as transport vectors. Okay, if it is temperature, we call it as thermal conductivity. If it is velocity, we call it as viscosity, and composition we call it by some other property. Okay, diffusion coefficient we call it. So these are the basic understanding of the definition. I hope you are able to understand. So these are the properties which actually are responsible for the quick or slow response of temperature change or velocity change or composition change in a material. Okay, so now in this particular class, we will try to understand how do we calculate or measure this thermal conductivity, viscosity, and diffusivity. Okay, these are the three things we are going to learn in this particular module. Let us understand what are thermophysical properties. So these are the properties which are affecting the transfer and storage of heat that vary with the state variables like temperature, pressure, and composition, and of other relevant variables without altering the material's chemical identity. So the important point is it doesn't alter the material's chemical identity, and the state variables like temperature, pressure, and composition, any one of this may be changing, and these are the properties. All these properties will affect either the transfer. So this transfer will be the transport property, and sometimes it stores the heat. Okay, Cp, we can say that this is Cp, this is K, this is the Cp, the storage of heat, how much rho Cv or rho Cv we'll call it as, okay, rho C. Okay, so this is the storage of heat. Okay, this is the storage of heat. So how this are all comes under thermophysical property. So If it is only dealing with the transfer of certain property or energy, we call it as transfer properties. And sometimes if it is also dealing with the storage of that energy or transferring of that energy because of the changes that are happening in the state variables or outside variables, state variables, the particular material state is being altered by the temperature, pressure, and composition. So the relevant variables without altering the material's chemical, there is no change in the material's chemical identity. It remains the same. Only thing is what are those properties which helps in the transfer or storage of capacity. Those are called as thermophysical properties. So under this, transport properties will come. So thermal conductivity, diffusivity, heat capacity, which is also storage of heat, thermal expansion, thermal radiative properties, viscosity, diffusion, surface and interfacial tension influence. All these will come under a particular part. Okay. Any doubts in the definitions of this? Okay. So this particular class, we will be looking at the first foremost important thing, which is what we call it as thermal conductivity. And later we will slowly move on to the other parts such as the viscosity measurement, which you will see in the next year, third year lab, you will see that. Now, why these are important, sir? Why we require this? When temperature measurement or heat transfer, that measurement of temperature becomes very, very important. And in your BME or basic mechanical engineering course, you might have studied the first Fourier's law of heat conduction. So how does this Fourier's law of heat conduction has come? It has come like the rate of heat transfer Q dot is directly proportional to the surface area. Is directly proportional to the temperature gradient. Is inversely proportional to the thickness. Okay. So now there is a thickness over here. What they have done is they try to give different known heat flux on one side, and they kept on going. Initially the area is only up to this, later up to this, and later up to this. Okay. Now you can see. So when the surface area for the heat flow is going on increasing, the heat transfer is going on increasing. When the temperature difference between these two, T1 and T2, on this side is T2. If this goes on increasing, then obviously the heat rate of heat transfer also increases. So the greater the temperature gradient on one side, the temperature is higher, and the other side it is lower. How much it is increasing, the better the heat transfer is. Correct. The third one is if you go on increasing the thickness, the time taken for the heat to flow also increases. Therefore, if you want to have a better heat transfer rate, the thickness of this plate has to be lower. So after doing some number of experiments, they have come out with a particular empirical formula, which is Q is directly proportional to A delta T by delta X, and the proportionality constant they used, which is actually governing the rate of heat transfer, they have called it as a transport property, which we call it as thermal conductivity K. And there is a negative signal which says that the temperature gradient is happening in the opposite direction. So then, therefore, we will get the Q as positive. Can any one of you tell me why this negative signal is there?
Sir, to compensate the decrease in temperature, sir.
Yeah, decrease in? No, why?
Temperature,
How do we what it will compensate? See, for example, if the higher temperature is on this side, okay, we are giving a heater on this side. So obviously the temperature will be higher here. T1 is higher here. And this is T2. Okay, on the other side, where we are measuring the temperature at the other end of the plate thickness, we are finding the temperature. Let it be T2. Now you write down the gradient here. T1 minus T2 divided by 0 minus L. Correct? So if suppose if you are taking delta X, 0 minus delta X. So therefore the temperature gradient is always negative. Okay, in order to make it positive, we are putting a negative value. Clear?
Yes, sir.
Okay, that is the reason why we are keeping a negative here. Otherwise, the heat transfer will become negative. And what do you mean by negative? If heat for a heat transfer is negative, we have the conventions that we use generally. Heat given out is positive or negative, or heat taken is positive or negative, based on what we are
Heat.
considering. Yeah.
He taken positive, sir.
So that can be anything. If someone takes in the other way, it will be gone into other way. So in what way? In general, it is heat taken is positive, we will take, but in general it can be changed also. But nobody will do that. But in general, that is a convention that we use. So we want to make sure that the heat transfer by conduction is positive. So just for making that, you have for this. Okay. So here the important property, what we call it as K, is the proportionality constant called thermal conductivity. All the other things I can measure. Q I can measure based on the current and voltage that I'm giving. So from that I will be able to find out the Q. Delta T, with the help of a thermocouple temperature measurement, with the help of thermocouples I can measure. Delta X I can measure by means of a scale. Area I can measure with the help of a scale. But how do I measure the thermal conductivity here? Okay, let us understand the thermal conductivity units are watt per meter Kelvin or watt per meter degree centigrade. Okay. So let us, can you give me an idea before going into the actual apparatus? How do we find out K? So from the mathematical equation, if you see, you have Q, you have K, you have A dt by dx. In general, in the academic books and all, while solving this expression, they will give you K, they will give you A, they will give you the temperature gradient and thickness, and they will ask you to, after this, they will allow us to find out Q, correct? Q is what they will be able to find out. Okay, since one unknown. So in this equation, we need to find out K means all other unknowns has to be known. That is for sure. So let us take K equivalent to minus Q into dx by dt by A. Correct? Are you following or not? K equivalent to minus Q dx by dt. This is the basic thermal conductivity equation. So what are the things that we need to know? Q we have to know, dx we have to know, area we have to know, and temperature gradient we have to know. So that means if I know Q, can I find out Q or not? So let us please try to open your mouth. It's an interesting thing. Guys, are you there or not?
Yes, sir.
So if I know Q, then can I find out the other property like thermal conductivity K? Like, it's possible or not?
Yes, sir.
Yes, sir. Possible.
Possible. So let us try to. I'm just giving an example. Can we devise a particular experimental setup for finding out K from the equation? Today's class, let us think in those lines rather than telling the exact principle and all. Just start with thinking, how do we, because it's a very simple thing. There is a mathematical equation. And from that, we need to just.
Sir, I got one idea, sir.
Yeah, tell me.
Sir, thermal conductivity is a material constant, sir. So, whatever material we want to have, we will convert it into sphere, and then we will compare with the black body radiations. From there, we will calculate the Qs, and we will already have the area.
How can you tell me that? You want to say that emissivity you want to find out, emissive power equal to, that is what you are asking?
Yes, sir.
How do you measure the radiation there? Emissive power you have to measure, no? For that, sigma
Yes,
T1 minus T2 power 4 you need to have. Epsilon sigma T power 4. Is that what you want to say?
Yes, sir. Sir, but
how do you get thermal conductivity then? Because you are finding out conduction, which becomes important in conduction principle. Whereas what you are saying is in a radiation principle where conduction is not at all required. So conduction is different from radiation. You understand? Radiation is a
Yes, sir.
surface phenomena. From the surface, if there is no medium, heat will transfer. That is what you are trying to find out. Whereas conduction, if you have this medium inside, from the center of, if wherever you are keeping from this material, there is a heat transfer. If it is a solid, the heat transfer will take place through lattice vibrations or the free electrons. If it is a liquid, by the movement of the molecules within the liquid or fluid, it will happen. Okay, so simple, think from these lines. What you need to find out from the expression. See, just coming to the class and sitting and by-hearting, that will not solve your, that is not the purpose of a particular class. So think of it. I mean, I am not going to start anything unless you find out a way to solve this particular setup, because it's very simple setup that you can make. So for a water,
Sir,
yeah,
let's assume that we take some known amount of heat and allow it to pass through a given material.
correct. So what I'm
And
trying
then-
to do is let us assume whatever you are saying. So this is the material that I'm finding. So let us take a slab. Okay, let us take a slab. Okay, this is for this material. I want to find out what is K. Okay. Now what you are saying is you are trying to give a heat flux of known capacity. Okay, you are giving a known capacity. So you are giving the voltage and current of known thing, and it will come to the one of the sides. Yeah. Next. Next.
Then because we have taken the material of known dimensions, we'll be knowing all those, sir. Area and thickness.
Sabash. Now K
Then-
equivalent to, you have Q, you have A, correct. Sorry, you have dx, that is the thickness, this thickness. Okay, and then you have the temperature gradient or temperature difference. So what is T1? How do you find T1? How do you find T2?
So because we have discussed the several temperature measurement
So
instruments.
the simplest is what thermocouples or thermistors I will keep at this location, or do you want to keep at all locations?
At this location.
No, many locations you have to keep. Otherwise,
Okay, to get some average value.
average value, whether you are getting the same thing or not. How do you know? So on each surface, on each side of the surface, you are having some at some locations. Now the average value you will take, you will get the temperature difference now. Okay, and area, which area you have to take?
The incident area.
Cross section.
Perpendicular to the heat flow. Okay, the area which is perpendicular to the heat flow. So this area or this area. Okay. Okay. So now you are having this expression. From this, I can find out K or not.
Yes.
But if you look at this expression, is this a one-dimensional equation or two-dimensional or three-dimensional equation?
One dimension.
Correct. It is a one-dimensional equation. Now, whatever the heat that I am giving on this side, will it leave from this edges or not?
Yes, sir.
So how do you take that into account? So it is a three-dimensional heat transfer that is happening. We are assuming that if you take the thickness is very low compared to this height, compared to this width, if the thickness is pretty low, we can assume that it is a one-dimensional thing. But nevertheless, we always have some kind of heat transfer that is happening through the edges because of the temperature difference between the edge here and the ambient air, from here and the ambient air, from here and the ambient air, from bottom and the ambient air. Correct? So what do you do? What do you want to do to arrest that? You want to arrest it, right? You want to have a one-dimensional heat transfer. Only heat has to transfer from this side to this side. I don't want heat transfer to this side. I don't want the heat to transfer to this side. Okay, suppose let us take this as X, this as Y, this as G. I want to arrest this Z direction and Y direction heat transfer. What can be the possibility?
Insulation, sir.
Insulation. Very good answer. If you put insulation, what happens? It will completely arrest the heat transfer. Will it do that? If you put an insulation, there is absolutely no heat transfer that will happen.
Maximum extent it can, reduce the heat transfer.
It reduces, that is understood. But will it completely? That means the temperature of the insulation is different from the temperature of the body. So when there is a temperature difference, will there be heat transfer happening or not? That means what I want to say is, suppose you imagine that this is a two-dimensional. From this side I am giving. Okay, I've kept some insulation over here. Okay, I've kept some insulation from here. Now I am giving a heater and heating it. Do you expect the temperature here and here to be the same? 1, 2, and 3 location, right? And all the 3 locations you have the same temperature, or it varies? If I give an insulation.
Sir, it depends upon the heat flux, sir. If if heat flux is concentrated, then it won't.
I am giving a heat flux like this, for example. I am giving the heater this. This is the heater. This is the width of the heater. Now you tell me.
It will vary, sir.
Then it will be different, sir.
It will be different from here to here. There is a temperature difference, and this is temperature difference. So even though there is a variation in this direction, x direction, we also have a variation in the y direction, again two-dimensional. Okay? Z may not, if you put an insulation over here, again there will be a z variation, correct? So that may not be, that can be a solution, but it may not be a very accurate one. Agreed? Are you agreeing with me or not?
Yes, sir.
Yeah, it can be a solution. Definitely, if you have that, you can do that, but still it will not give you a very accurate answer. So just think in a different way. What I want to have for solving this particular problem? What is the requirement? I want to have one dimension. That means my heat has from this side, on this side, everywhere it has to be one, the same. How can I do that? You are very close. Just think and answer. The only reason is,
Sir, we have to make sure that heat is uniformly distributed, like how we provide the heat.
How can we do that? That's what I'm saying. At the center, we have a heater which is maintaining the temperature at the center to be T1. At the edges, if you keep an insulator also, its temperature is different. Therefore, a temperature gradient, that means a temperature difference along the y-axis will happen, and a temperature along the z-axis will happen. So if I want to have the same temperature all along, what can be done at the edges? Very simple question. If I keep an insulator, the temperature is different. So when there will not be any heat transfer, when the temperatures of the two bodies are same, correct? So if I want to have the same temperature from here to here, what can I do at the edge? I've given my answer.
Sir, why can't we take some spear sort of thing with heater at the center?
No, don't think of the center, just leave it. But edges, what can I do? That's what, think simply. You have a temperature T1, you have a heat flux which is maintaining a temperature of T1 at the center. And I want the temperature to be the same at the edges also. So in general, if there is a different temperature at the edges, automatically the temperature gradient will happen. So if I want the same temperature at the edges also, what can I do at the edges of the particular box? If I put a heater of the same heat flux or temperature at the edges also, can we have uniform temperature and will it make a one-dimensional case?
Yes, sir, but it will violate the Fourier's law also, na, sir.
Why? What? How it will affect it?
Sir, because at the edges we are providing heat, then we have to consider.
We are not providing any heat. Why heat will come? You are maintaining the temperature to be T1. So when the temperature is T1 here and T1 here, how heat transfer will take place? For heat energy to transfer, there should be a temperature difference, and there is no temperature difference here. Okay. So at the edge also, if I'm keeping the temperature as same as T1, on this side also T1, on this side also T1, and at the bottom also T1, then the heat that comes in will be on the surface, complete surface area, this area, whatever we have. That will be, I'm just trying to mark it, this area is all maintained at one particular temperature. And on the other side, it will be a different temperature. So this side it is T1. Since this side I have to maintain at T2, so what I can do, I can send some water at cooling temperature of 100 degrees or constantly maintained temperature cooled water. So that means we will have a hot bath which is maintaining the water temperature to be 5 degrees centigrade, for example, or 8 degrees centigrade or 10 degrees centigrade. If I'm sending this side, the cooling jacket I am providing, and it is always supplying 8 degrees centigrade of water. There is a temperature T1 here, and on the other side we always have T2 temperature because there is a cooling body. So because of that, your temperatures are being controlled, your heat flux is being controlled, and it is completely made one-dimensional. So this expression can be made, and you can find out the thermal conductivity. Correct? So this simple setup.
Sir, but then it means that like at certain length ranges we have to change our device, sir, because T1 and T2, sir, at a particular T at a particular location won't be same, sir. Won't be same, sir. At particular locations, you have to change it. So you are telling us, sir, like suppose from the starting, like 100 degrees centigrade, let us take, and that we have 50. At somewhere middle point, we'll be having 75 degrees centigrade.
The heater that you are giving is only at the edge. You can have a very thin heater plate. You don't have to put a heater plate of this particular width. If you are putting a heater plate of this width, then as you are saying, the top temperature is different from the internal temperature, sir, there will be heat also. But I am keeping a thin plate of heater, strip plate of heater or something. So what it does, it is having very thin and it is only heating at the center. The edges also I am keeping the same heater. So this heater is having T1, this bottom it is having T1, and this bottom it is also having T1. So what happens at there? It will be maintained at the same temperature. That is what I am saying.
Sir, the problem is with the square cross section only, sir. Here we are
I
taking
am not able to understand what exactly your point. Can you say?
Sir, the problem is with the cross section area, sir. The
What
cross section area? Sir, here here we are taking squared one, sir. But heat flux distribution won't be like in spherical form or something like that, sir.
What? Heat transfer will not be.
Sir, you are taking at the edges. Like at edges, we are telling means so by suppose we are taking the edges, it is differing the temperature as we are moving upwards. But then means it won't be same at the remaining edges, no, sir.
We are keeping the same heater at all the edges on 4 sides, top, bottom, left, and right. Okay.
Yes, sir.
So if it is T1 all the sides, why it will vary? That I didn't understand why you are saying. So if you are keeping T1
yes, sir,
here,
yes, understood, sir.
T1 and here and there. Yeah?
Yes, sir, understood, sir.
Yeah, yes. You don't get Taman. If you are not satisfied,
yes,
we will see. Yes, you understood, right? So
yes,
obviously what happens is that there is a transfer because the temperature difference is from this side to this side. So only heat will be in the x direction. That is what I'm saying. Only in that particular case, we can make this equation, you utilize this expression. Okay. So this particular methodology is called as what we call as guarded heat plate apparatus. GUARDE, the guarded heat plate apparatus, which is used for measuring the thermal conductivity of metals which are having low thermal conductivity. Why low thermal conductivity? What can be the reason why we are going for a low thermal conductivity? Simple. If the thermal conductivity is low, what happens if I'm giving a heat flux here? The temperature difference will be more or less, because K is a property which actually helps in transferring the heat quickly or slowly. It is responsible. So if it is low means it is not sending the heat energy very quickly to the other end. Obviously there is a temperature difference which is higher. So by using the measurement devices, To measure high temperature differences is easier compared to very low temperature difference. If it is having very high thermal conductivity, it tries to come to the same temperature very quickly in the steady state condition. So the very small difference, if you want to measure, you need to have accurate devices, and therefore it becomes different. So therefore, this device, whichever I am talking about, guarded heat plate operators, is useful for measuring the thermal conductivity of metals or non-metals, generally non-metals, because metals will generally have high thermal conductivity, of non-metals which are having low thermal. Clear? Most of the material property K is already measured and is given in different data books. Okay, for aluminum, copper, different materials, they've already found it. But why it is required? Suppose if you are encountering a new material, you have developed a new material. The first and foremost thing, it may have very high structural strength, but you always have to tell them, because composite materials, 2 or 3 different materials they are combining to form a new material. So when you form this composite material, the first and foremost thing you have to show is, you have to make sure that what are its thermophysical properties, what are its structural properties, you have to define first. Then only you can use it for a specific purpose or usage in the particular application. Clear? So therefore, the knowledge of measuring the thermal conductivity is very, very important for you as an engineer, as a mechanical or thermal engineer. Okay, before doing the I just started with how can we define or design things. So it looks a very simple expression, but look at the complexities that are coming in. You have to take out the 3-dimensional heat transfer or 2-dimensional heat transfer and make one uniform heat transfer. So what you are trying to do is, initially they might have kept the insulation and then they made this experimental setup, but later somebody might have come, and when they have done experiments and when they have simulated with the thermal conductivity, they might find it different. So they might have felt it to, no, whatever you are finding with the help of a thermal conductivity from the measurement apparatuses may not be correct. So this can be calculated by means of K, which is a measured value. You can keep, and by a mathematical or analytical solution, you find out Q. But when you actually measure it, it may be different. So then the question comes now, how do we improve the uncertainty? How do we measure K measurement can be improved? Then they might have come up with a solution. Then no, there is a insulation that is not actually creating the one-dimensional. Let us keep it another temperature, which we call it a sample heater or something, which is having the same temperature. So if you keep that, now since the temperature on both the sides are same, it may not affect the central or dimensional flow. So therefore it will become unidirectional or one-dimensional. And when they compared these two expressions, they might have come very close. So therefore they said that this apparatus setup can work better for measuring the thermal conductivity. Okay, so many things are there. Again, they are able to define what are the disadvantages if it is only for K thermal conductivity, low thermal conductivity, because the temperature difference will become more, which is become easier for normal devices to use, like thermocouples, which are cheaper in nature. But if it is very low, if it is very high, and the temperature difference is very low, you need to go for very precise instruments, which will be costly. So all this comes into picture. Now, while measuring it, you may be asking, sir, at what time I have to measure the thermal, the temperatures? So in the same experiment, what time, sir? Initially, as soon as I give you the temperature, I have to measure, or I have to wait and measure it after a certain period of time. What is that time? 1 hour, 2 hour, 3 hour, 4 hour? What is the time? So why we have to wait for time? Because we want to attain this to a steady state. Initially, when I have a copper plate. When I give heater, some heating through a heater plate, even though the center part is only being heated, the whole plate will attain the same temperature, because this thermal conductivity is higher on one side. I'm talking about one surface, on this surface. It attains certain temperature, same temperature. For that to happen, it takes some time. That is its steady state. Similarly, from here to here to transfer, it takes some time. So therefore, we have to wait and take the temperature readings on either sides after varying for certain time. How do you know the steady state? So that is what we call it as a steady state. What do you mean by a steady state? Steady state means that the spatial variation of temperature may be seen. Steady state heat transfer I'm talking about, steady state temperature. So spatially, from here to here, the temperature may vary, but with respect to time, in the morning, the temperature here is 100 degrees, here it is 50 degrees. In the night also, the temperature is 100 degrees, here it is 50 degrees. So spatially, the temperature is varying, but temporal, that means time, it is not varying. Okay, so such conditions, if we acquire, that is called as steady state temperature. So there are two ways of measuring it. One is the steady state method. So that means performing a measurement when the temperature of the material measured doesn't change. So even you take after, suppose you are assuming that it attains a steady state after 2 hours. If you measure that after 2 hours, 4 hours, 6 hours, 8 hours, the result will be the same. But before 2 hours, if you do, the result will be different. 1 hour will be different from 1.5 hours. So there is one method which we call it as a steady state method. Another thing is transient method, which means it performs a measurement during the process of when immediately when the heating starts. Immediately, if you are taking the measurement, so those kind of measurement methods, we call it as transient or unsteady methods. Clear? Now, this is what I have talked about. This is the basic steady state guarded hot plate apparatus, which is for non-metals solid samples. You can see here, there is a sample here. We have a sample over here. And this is the guarded hot plate. So this is the actual heater that we are using for heating it. And there is a guard over here on the two sides. So these are also heaters only. Okay, these are also heaters only. And this is the sample, one on the top and one on the bottom. So why we have to put one on the top? It is enough, no? Why there should be another one at the bottom? You can leave it, no? There is a guarded plate, guard on two sides which are maintaining the same temperatures, right? And this is a sample that we have. Okay, this is the sample for which I need to find out the temperature difference. And this is the cold surface, which may be cooled by a fan, heat sink, like this. And on the peripheral side, we have this insulation. Why the bottom also will have the same thing? What is the requirement? If it is providing heat through this, it will go through this and this, on the top and the bottom. Anyhow, on this sides, it will be eliminated because there is a uniform heater that is forming on these two sides. Now, if I don't provide a sample of the same sample here, the temperature of the fluid or the solid on this side is different, has a different property of thermal conductivity from this side. So if it is having more thermal conductivity, so the more amount of heat will be transferred to this side and the less temperature will go this side. So in order to make it uniform, on this side the same heat transfer, on this side the same heat transfer, we are making two types of samples, and we are trying to measure the same amount of cold liquid is sending through this cold surface and this surface, and on these sides we are keeping it insulated so that we will be able to find out what is the surface temperature. So exactly the same things we have kept, and we have thermocouples kept on the sample surface side for finding out delta T, and here this is delta T1, T2, dx. This particular thing is what we call it as area, and I know what is the heat flux that I'm giving through the guarded. Okay. So this is another just a view of the same guarded heat plate apparatus that will be used. So we have a samples on the top. We have the heaters. Main heater is here, and we have the guarded heaters here. So guard heaters. Okay. So those two are maintaining at the same temperatures, and then we have the coolant that is coming in and coolant that is going out. So after taking the same temperature from this side, it will move, the fluid will move out. We will find out what is the temperature of the fluid. Similar coolant in, coolant out. Whatever the coolant that is coming in will be the same temperature at this, and there are two sides which are actually maintaining an insulation. So this is basically guarded heat plate. This is very important. That's why I have spent a lot of time on this. Now, how this guarded heater plate will look like? You can see over here, there is a main heater you can see here on 4 sides, you can see here there is a main heater which is 200 by 200 mm. Okay, and there is this guard heater which is 50 mm wide. Okay, and you can see that the thermocouples, there is a 2 mm gap all around. We are having a small gap. We are not actually directly hitting it. We are having a very small gap all around, and then there are thermocouple junctions which we are maintaining here. So this is how the guard heater will look like. Okay. Similarly, suppose if we have radial flow heat flow operators for some liquid sample. Suppose we have a liquid sample. Okay, how do you find the thermal conductivity for a liquid? Okay, so let us stop for today. I think thermal conductivity comparators. Okay, let us come to the radial heat flow operators a little bit later for liquid sample. Let us find out a comparator kind of a thing. For example, this is another kind of a method for finding the thermal conductivity of a material, comparing it with the known thermal conductivity of another material. So the principle here is slightly different from what we have seen from the previous case. What we will just try to understand. We have a heater over here. There is a hot surface over here. Okay, and this side it is insulated. This side it is insulated. And what I'm trying to do here is we have a standard reference material for which the thermal conductivity is low. Okay, and this is the material for which I need to find out the thermal conductivity. This particular A is a standard reference material for which I know the thermal conductivity, and the material B is the material for which I want to find out the unknown thermal conductivity. So this thermal conductivity I didn't know. This is a newly fabricated or devised material, formulated material for which I am finding the thermal conductivity. So now this one I know the thermal conductivity of fresh because we have done some experiments by means of this hot-guarded operators or something. I know the thermal conductivity of this material. So with the help of comparing these two things, will I be able to find out the thermal conductivity of this material or not? That is the challenge over here. Now we have the thermocouple junctions kept over at different locations, and LA is the distance that I'm taking, and LB is the distance I'm keeping in between the thermocouples. Okay, now this kind of material, this kind of method, we call it a thermal conductivity comparator, which can be used for metals. The other one is for non-metals. Okay, there that is different. For non-metals, we are using guarded heat plate. It is for metals. So it is like comparator. That means we are kind of comparing the two different materials in which one is known material and other one is unknown material. So you know that Q is equivalent to, what is the heat transfer that is happening in this particular thing? QA equivalent to minus KA, A dt by dx, correct? QA is equivalent to minus K A area of it into dt by dx. So I can find out what is the temperature here and here. I know the thermal thickness, and I know what is the area of this surface, and I know what is the thermal conductivity by some other measurement. So I know QA. Under steady state condition, when you are keeping two materials, compound materials, okay, if you are keeping like this, whatever be the thing, QA will be equivalent to QB under steady state conditions. QA will be equivalent to. Since I know QA, I also know QB. So that whatever heat transfer that is happening, QB, which is equivalent to minus KB area of the material B into dt by, we should write dt by dy, because if I am taking this as y or x, it depends, dt by dy, dt by dy. So since QA is directly formulated from the expression, Okay, so this will become equivalent to QB, and area of the material, unknown material, we know. The temperature difference between the unknown material because of suitable thermocouples I know, and therefore I'll be able to find out what is clear. So this is the methodology that I will use to calculate the thermal conductivity of a metal. And the third one is the how do you calculate for liquid sample as well as for gas sample. This we will try to find out with another simpler figure, which I have kept the old one. So as in tomorrow's class we will decide, and Friday's class we will decide the other two things. Okay, how do you measure, which is very important, because you need to understand those two things. How do you measure the thermal conductivity of a liquid? How do you measure the thermal conductivity of a gas? That also becomes very important. Now, one of the way that you can do is the same material process can be done. However, we are doing the same thing can be done with sample. Okay, process is same, but what will be the difference in this? Suppose if it is a liquid over here, if a liquid, imagine a liquid is over here. What happens when you heat it? Will it by conduction or convection? Suppose you have a water in a pan, okay, water inside a pan, and you are heating it with the help of some heater. Okay, you are heating it. So what happens when you have a beaker and inside that some liquid in there? The water at the bottom gets heated up, and its density become lighter because the mass transfer will take place. This heated molecule will move up, forming a circulation within the cell, right? There is a movement that starts within the circulation that will start within the liquid. So that will give you Q equivalent to HA delta. So there is a convection that is happening. So therefore, it becomes heat transfer coefficient, not thermal conductivity. Now, how can I reduce the circulations that are happening? By having a lower and lower annulus, right? Suppose if the liquid is kept into this particular region, very small region, compared to this, and imagine that all the other are same. There is a heater, there is a guarded one, heater, guard heater, okay, guard heater, and on this side you have this cooling plate, and on top you have insulation, for example. Okay, so this same thing can be done. So, but it becomes easier when you have a circular cylinder kind of a thing. One is the inner circular cylinder and another one is the outer circular cylinder. And in the annular space, in small annular spacing, if we can provide these things, then it will be very easy to find. Okay, you can see over here there is a thermocouples we have kept. Okay, and you can see over here there is a heater plug on this side. We have a heater plug on this side, and then is another heater plug on this side. And there is a small annular gapping over here, narrow annular gapping, in which the sample liquid will come in. Okay, the sample liquid will come in and it passes through the smaller gap and then it leaves. Because it is a circular one, from the bottom it enters, and from the top to the circular gap it is going. Okay, around that you have a cooling water in, and there is a cooling water out surrounding in this particular outer cylinder. Clear? At the center you have this heater, which is what we are using for this, and you also have thermocouples. So from that you will be able to find out what is the thermocouples. The key here is this particular annular spacing, which is very much smaller than. Why this annular spacing has to be low? To avoid the convection currents, This is the method that we will use for finding out the thermal conductivity of. This is for liquids. How do you do it for a gas? We will see in tomorrow's class. Okay. Okay. So, any questions? I'll be happy to take.
No, sir.
I hope it is clear. Is it clear, guys? So this is how you have to think whenever there is a mathematical expression that is there, how slowly we can build up an experimental setup, and even then we will have some problems with the experimental. That means some uncertainties will creep in. So one by one you have to think logically whether it makes sense or not. So step by step you have to avoid the other things, and then you can build a very good experimental setup. So this is the thought process that has to go in. So always you have to, once you find out a measurement setup, you have to compare that with a standard procedure, whether how well you are able to get. With over a period of time, you have to check at different places. You have to check, and all these standard procedures you have to follow to say that your experimental setup is giving proper result. All right. I hope whatever I taught today is clear to you, and if you have no doubts, then I will stop at this point of time and we will meet in the next class. So today we have learned about measuring the thermal conductivity of metals, non-metals, and liquids. Okay, I will give you a nice neat figure for the liquids. It's a little clumsy, so I will give you another figure which is simpler to understand, and then for fluids we will find out. And then continuing the class, we have thermal diffusivity, viscosity, okay, and then calorimetry. So these are the other properties measurement we will have a look at. Any queries from anybody? Karthik, Vaishnavi, do you have anything to say? Charan, Hemant, anyone is having anything, please feel free to ask. Always there are 2 or 3 people who speak, Samarnath, Vilash, only those two. What about mid-mark, sir? That is the only question we will keep on asking. I told you at the start itself. I'm correcting it. Let me please give me some time. Otherwise, I may have to rush in. I have some other work happen, so I couldn't finish it. Sorry for not sticking to my words. But generally, this is what happens with me. I generally take some time to correct it. Okay, Sahib? This weekend, it's for sure. This weekend, I will definitely. Yes, we don't have any lab this Thursday, right? We have a holiday, correct?
Yes, sir.
So we're not having any lab. So how the graph is coming? Yesterday one student has actually sent me. It didn't look promising. So how others are getting? Okay, whatever you got, just look at the manual that I've shared with you. How well you are able to get it. You try to draw that in the graph. Okay, apart from that. Any more thing? Anything more apart from mid? Did I missed any LMS classes or anything? I have to put in LMS thing.
No, sir, everything is there.
Yeah, everything is there, right? So,
Yeah.
So okay. So if you are fine, sir, you want to share lab marks? Yeah, I can do that now. I will share you directly. I will share that. Will you be online or okay? Those who want to leave, they can leave. I will share those 4th and 5th LMS marks to lab marks with you.
5th and 6th.
Which one, Kalyan?
5th and 6th.
5th and 6th. Just a minute. Just a minute. Be online. Those who want to leave, they can leave. No, absolutely. Because I will have rather different works and then I will forget.
Hello, sir.
Yes.
Sir, the last point was actually like going out of the league, I guess. I mean, in the graph also, T lab, sir.
Okay. So
In
what is
T lab,
happening?
the last reading was going out of the league, sir. In the graph also, and like the discharge was around 0.7 to 9, and all the discharges were like around 2. So it was difficult to draw the
Exactly.
graph.
That
Like
is what exactly. That is whatever he has sent me. What I observed was the rating was not uniformly distributed. It
so
is
like
only in between
if
3.8
we
to 4.2 or something. Correct?
sir, is it okay if we don't mention the last point in the graph, sir? It would be better
That
for
is
us.
okay. That is okay. That is okay. Just make sure that the graph is neat. Okay. If you
Okay, sir.
don't have, but calculate, but don't show it in the graph. Okay.
Yes, sir. We did the calculation and we mentioned in the table, but yeah, we can skip in the graph.
Yeah.
Okay, sir. Thank you.
Yeah. This is CFT. Okay, I will just check and I will send you now itself. I finished that and I'll inform Kalyan. Okay, the lab marks I'm not able to find from him. Anyways, I will have a look at. Actually, he sent to me. I will just upload. I will send to your email, not for the LMS. I will send to your email. Okay. So thanks for attending the class. Please take care of yourself. We'll meet on Friday again. Right. Happy Diwali to all of you. Take care.
Thank you.